Hello, everyone. We're back again. So yesterday we read part of this paper, Titans, Learning to Memorize in Time. Learning to memorize at test time. And it's a juicy paper. It's some interesting stuff in here. It took us, I don't know, a solid, 15 minutes to read 2 pages. So we stopped right before we got to the section where they started with the math. That makes good sense. They start telling us there's some math involved. I'm going to back away. I need a fresh brain. We're here with a slightly fresher brain. I'm going to attempt to try and understand it. This could be a total failure, but we'll do it together. Someone can join the comments and say, what the hell? How are you so stupid? But this is how it looks like for me trying to figure out what this says. All right, so in this section, we'll discuss the notation and some background concepts that we'll use in the paper. We let this is the magic we want to know. X, what's that symbol? X, is that E? R, N, X, D, N. What do any of these mean? Look it. Okay, here's what we have to do. There's only one way to do this, okay? We got to open up the Jippity. Hey, Jippity. Up the Pro? Hit him on the Pro? Okay, let's upload from my computer. Oh, God, the picture of the devil. Explain what each of these math symbols are and how they might be related in this formula. We can spell everything wrong, it doesn't matter. So M is a neural network, which is not actually part of that original. A QKV be the query, key, and value of the attention mechanism. And M be the attention mask. Now notice this. This is a fancy M, and this is a more serious M. Fancy M, more serious M. Totally different. This is the attention mask. This is the neural network. It's going to take forever because I asked the Pro model. Why did I do that? When segmenting the sequence, we use SI to refer to the nth segment. Throughout the paper, we have used the notation and use subscripts to refer to specific elements of the matrix. Okay. Vector or segments. Actually, can I hide this thing? Yes, I can. That makes it a lot better. For example, we let Sij be the jth token in the nth segment. Okay, cool. The only exception is subscripts with T, which is reserved for the index recurrence over time, or the state of the neural network at time T. Given a neural network, fancy N, and the data sample X, we use NX, response, N star X, to refer to the forward pass with respect without weight adjustment. Also, we have used the notation and use NK to refer to the kth layer of the neural network. In the following, we discuss the backgrounds for attention and its inefficient variants, followed by a review of modern linear RNNs. Finally, we discuss the memory perspective of the architectures that motivates us to design Titans. So much above my pay grade. So much I'm never going to be able to understand this just in one little sitting right here. But we'll try. We'll hurt the brain. We'll see if we can get anything. And maybe next time on the next paper, we'll get a little bit further here. So if you see something like this inside a broader formula, for instance, a neural network layer or a linear transformation, it usually means you have n items, so data points. Each item is represented by the d-in features, d-in, so n items times each item individually. Hence, X is organized into a matrix with 1 row per data and 1 column per dimension. No, my chapstick. A common operation would be multiplying X by another matrix, W. ERD and D out to produce a new matrix. This is matrix multiplication. No. D out would be the dimensional of the output space. Each row of XW becomes a D out dimension vector derived from the corresponding row of X. Barely understand this. So X is a real value is a real value data matrix right here. N is the number of samples. I got that little N right there. Dn is how many features each sample has. When you combine X with the other matrices in the formula, that transforms and processes the features. Not really any smarter. Slightly, maybe. I don't know. It's about matrix. We know that. We know that AI is all just matrix multiplication, right? Okay, we got to go back and read the attention paper. I at one point, I thought I understood it. It took me a million hours of reading, and I thought I understood it. I talked to people for a million hours, but it's been too long now. Got to go read it again. The classic. There it is. Oh, yeah. Oh, no, they just gave us the ending. Come on, give me the actual paper. It's okay. Okay, so attention. Transformers, as the de facto backbone for many deep learning models, are based on attention mechanism. Given the input X, E, R, and DIN. Okay, here, watch this. How would you say the formula I'm going to attach the image again. Phonetically. Oh, I shouldn't have asked Pro. Let's go to 4.0. Okay, so given input X ER end in, casual attention computes output Y ER end in, based on softmax over input dependent key value and query matrices. Key value query matrices. Key value query matrices. Where WQ, WK, and WV are learnable parameters. Despite the power and effectiveness in recall, transformers need at least ND operators to calculate the output, resulting in larger memory consumption and lower throughput through longer sequences. Okay, so I definitely am still not understanding this, but we're on to something, okay? So we there's an inputs and there's outputs, right? And the dependent key value query matrices that we use are learnable parameters. However, when we use these as learnable parameters, we need at least the number of total parameters, or whatever n is here, what they told us before. Well, there's fancy neural network n, but there's also n, which they were saying here is the number of samples, potentially. So despite the power and effectiveness in recall, transformers need at least ND operators to calculate the input. Okay, the point is we looked at this, we could tell it, hey, check it out, we're going to need more operators because of the way this math formula works. You need more operators based off the samples. So larger memory consumption, lower throughput. Okay, kind of, because look at it's saying lower throughput for longer sequences. What is n? N is the number of actual sequences, which are always multiplying by d. What is d in this case? Well, they were saying d out earlier. Correct. Well, there's D in it, how many features each sample has, but D out would be the dimension of the outer output space. I don't know. We almost understood something. Okay, efficient attentions. To improve the memory consumption and throughput of the softmax attention for longer sequences, various studies focused on IO-aware implementations of attention. Dao, Di Fu et al. Dao, and then Dao did it again. Or it's two different DAOs. Designing more efficient attention mechanism by sparsifying the attention matrix. Oh yeah, this happened in 2021. In 2019, approximating the softmax. Ooh, that just happened. Or developing kernel-based linear attentions. Also hot new stuff. A lot of people working on that. Kernel-based linear attentions. In this part, we focused on the latter, linear attentions, where the softmax and standard attention is replaced with an alternate kernel function. Accordingly, the attention can be written as this. Now, what does that mean? No one knows. So watch this. I'm going to go here. I'm going to go here. I'm going to go here. I'm going to go to Pro. I'm going to go here. I'm going to go here. I need a faster workflow for this. Explain this to a dummy who only knows how to program and knows no math. There we go. Wait for that answer while we're learning more. Okay. So obviously now it can be written as beautifully as this. Yes, you guys were using this before. Elementary. So don't you guys know? That's never going to scale for longer sequences because remember, the transformers need at least n times d operators to calculate the output. And remember, n being the number of samples. So when you get these longer sequences like this, you're just going to end up paying for compute out the ass. I don't know if that's or it gets worse actually. Okay, modern linear models and their perspective memory. As discussed earlier, one can define learning as a process for acquiring efficient and useful memory. Building upon this, one can see the hidden state of recurrent neural networks, RNNs, as the memory unit, which the model aims to compress the information into. Accordingly, in a general form of a recurrent neural network, the hidden state can be treated as a memory unit, and the recurrence process can be split into a read and write operations in the memory unit. That is, we say XER and DIN be the output, MERD is the memory unit, and URDIN is the output. The general form of the recurrent neural network is defined as here's a write operation, here's a read operation. Okay, lovely. What do you got for us? Okay, so in this perspective, the recurrence formula of linear transformations is equivalent to additively compress and write keys and values into a matrix value memory unit MT. So what we're really doing here is we're additively compressing, is equivalent to additively compress and write keys and values into matrix value memory unit, MT. Therefore, when dealing with a long context, this additive nature of the process results in memory overflow, significantly damaging the performance of the model. To address this, studies have focused on two promising directions. Adding a forget mechanism. Several studies have presented adaptive data-dependent forgetting gate mechanisms for linear models where it can erase the memory when it is needed. As such needed models, we refer to GLA, LRU, XLSTM, Mamba 2, which the later is also connected to a decriticized version. Oh boy. And applied, I'm so stupid. Discretization. Discretization is the process of transferring continuous functions, value, models, variables, and equations into discrete counterparts. Cool. No, that goes in fun, not music. Okay. Oh boy, let's try and read this paragraph, and then I'll go check out my Jippity. Okay, to overcome the additive nature of the memory write operation in traditional current models, Widrow and Hoff presented the delta rule. Why does it say 1988? Whoa. In which, before adding memory, the model first removes its past values. To enhance the parallelize in training and scalability, presents a fast parallelizable algorithm. Finally, very recently, Yang Kautz and Haramzadeh improved the delta nets by adding a forget gate. Okay, wow. They're really going to tell me like I'm a programmer here, okay? Here's an informal code or any way that takes the formula for linear attention. Imagine you're trying to compute weights for each item and then taking a weighted sum of values with a twist that makes it more efficient than the usual softmax approach. Okay, so the usual softmax attention in plain coding terms. You have three arrays called Q, queries, K, keys, B, values. When you want to compute the output of position I, you have to measure how similar Qi is to every Kj. Typically, you do something like this. When you want to compute the output at position I, we need to see how similar Qi is to every Kj. Typically, you do something like this. You say weight J is going to be equal to an expression, some sort of function that is going to be Qi dot Kj, which is going to probably figure out how close these things are. And then you normalize all these weight J's so they sum to 1. Finally, you multiply the weight J by the corresponding Vj, and then you sum them up. That's the standard attention or attention softmax, the traditional way. This is not efficient enough at all for our big old giant context windows. So switching to a kernel for linear attention, replacing the expression with a kernel. Instead of this, you could compute something like this, phi. Now, this is just some function you pick to measure similarity. Okay, great. So when we're seeing this thing originally, this is just a function to measure similarity. So when you're seeing this originally up here, this saying, hey, dude, give me how similar these things are. Look at it's happening again. Look at it's happening again. Look at it's happening again. Is that what it always is every single time? According to Jippity, it is. Jippity can't lie. I could all be wrong, but there's so many things to learn. I cannot learn any one base fundamental thing to like build up from it right now. And this, you just kind of, sometimes you gotta like run through the forest, bang your head against a bunch of trees, understand nothing, and then I realize, damn, I gotta go back to square one. But we'll get the stuff we can understand later. Back to code. I code. I'm just hooking APIs up. I'm not actually writing any of the fancy stuff. Okay, rewrite the sums in a more efficient way. Because you can factor this into this and this, then this is the discretization. Jeez, that's a tough one. Because you can do this, I think it's discretization. That's what it feels like after reading the one sentence of a Wikipedia article. It can be organized like this. In the code, that means you could pre-compute, okay, and then you could do this. This trick can greatly speed everything up by doing everything pair by pair. Okay, that's why it's called. Okay, so we still do the weighted sum of the values. We get the weights using a kernel function, which can be split into two separate pairs. So that we can parallelize it because we're taking one bigger function, we're splitting it into two separate pairs, we're checking some distances. And since we can do those two things split at one time and then bring them together at the end, that means that it can be parallelized. That split let us handle it in a more efficient linear way. We don't have to recalculate from scratch every I. There you go. That's why it's called linear attention. You could reorganize the calculations, they only grow linear with the sequence length rather than quadratically. That's why it's called linear attention, because it grows linear, not quadratically. Linear is meant to be a brag. Okay, quadratic, that's lame. If you're comfortable doing code ellipse and array, just picture an array by array transformation plus some fast dot product cumulative sums instead of express plus softmax. Okay. That actually helped a little bit, okay? Still very stupid, but actually helped a little bit. So modern linear models in their memory perspective. As discussed earlier, one can define learning as a process for acquiring efficient and useful memory. Building upon this, one can see that the hidden state of recurrent neural networks as memory units, which the model aims to compress the information into. I've read this already. But hey, see, I at least knew I read it already because I actually read it. Did I understand it? No, but I was like, I read these magic words before. Okay, so let's read memory modules. Memory has been one of the core parts of the network design systems by all these different people. The idea of seeing linear layers as key value associative memory systems backs to fast weight programs, in which dynamic fast programs are incorporated into recurrent neural networks to serve as writable memory. The two learning rules of Hebbian and Delta are the most popular learning rules for fast weight programs, which have been extensively explored in various studies. A bunch of names. All these models, however, are based on momentary surprise, missing the token flow in the sequences, and most of them lacks a forgetting gate, resulting in poor memory management. We further discuss the connection of our architecture with recent models here. Learning to memorize at test time. Okay, that was the little preamble. Let's see if we can understand any of the actual, what the magic is. To overcome the lack of long-term memory and to enable the model to learn and forget and retrieve information, in this section we present a neural long-term memory module, which is a meta model that learns to memorize at test time. We first discussed the motivation and the design of the neural memory. In section 3.2, we discuss how architecture design can benefit from a fast parallelizable training. Finally, we augment architecture using persistent memory module. Now, one of the things is like, what does test time mean in this case? And one thing is like, if you're asking a question to me, if I answer it, then deciding at that point when I'm answering it's some information that I would want to recall again, and then saving it to long-term memory, maybe that's what it is. So once you start actually, like you take a short-term memory, once you start bringing it up multiple times, then it becomes a long-term memory. You're not deciding to make it a long-term memory on first input. I don't know, just guessing, trying to figure stuff out. So, to design a neural long-term memory module, we need a module that can encode the abstraction of the past history into its parameters. An example of this can be LLMs that are shown to be memorizing the training data. Therefore, a simple idea is to train a neural network and expect it to memorize its training data. Memorization, however, has always been known as an undesirable phenomenon in neural networks, as it limits the model generalization, causes privacy concerns, and results in poor performance at test time. Moreover, the memorization of the training data might not be as helpful at test time, in which the data might be out of distribution. We argue that we need an online meta model that learns how to memorize forget data at test time. In this setup, the model is learning a function that is capable of memorization, but is not overfitting to the training data, resulting in better generalization at test time. Learning process and surprise metric. The surprise metric. We learned about this before. If something is surprising, we're more likely to want to commit it to memory. This is how humans work too. Something wild happens. It sticks in the brain a little bit more than the mundane. Now, the key idea to train a long-term memory is to treat its training as an online learning problem, in which we aim to compress the past information into parameters of our long-term neural memory module, MT. As discussed earlier, an event that violates the expectation is surprising. It's more memorable for humans. Inspired by this, a simple definition of a surprise for a model can be its gradient with respect to its input. The larger the gradient, the more difficult the input data is from the past, the more different the input data from the past data. Accordingly, use the surprise score, we can update the memory. Okay, obviously, this is encoding surprise. Surprise. It's so obvious what it is. This surprise metric, however, can result in missing important information that comes after a big surprising moment. That is, the gradient can become extremely small after several surprising steps, leading to stocking in a flat area, local minima, and missing information about some parts of the sequence. From the human memory perspective, an event might not consistently surprise us through a long period of time, although it is memorable. The reason is that the initial moment is surprising enough to get our attention through a long time frame, leading to memorizing the entire time frame. To improve the above surprise metric, we break the surprise metric into past surprise, which measures the surprised amount at the very recent past, and momentary surprise, which measures the surprise of incoming data. This obviously this is just how humans work too. We always have to divide things into past surprises and momentary surprises. Interestingly, this formulation is similar to the gradient descent. So momentary surprise is something that is just like interesting, that moment over moment. It's not like a big shocking thing. Like some new thing has happened. Now we're in the new shock state. Now we're getting little bits of shock at your first concert. Oh my God, I remember the beginning of it is like insane. But now you're in the concert and experience all these things, but you're slowly becoming more comfortable. That's the momentary surprise. I think that's what it means. I don't really know. Interesting, this formulation is similar to the gradient descent where ST is the momentum element. Therefore, the momentum here acts as a memory surprise across time sequence length. In this formulation, the term NT is a data-dependent surprise decay, a function of XT controlling how many surprise decays over time. And the term 0T is controlling how much of monetary surprise should be incorporated into the final surprise metric in a data-dependent manner. This data dependency is particularly important in this design. While surprise of previous tokens might be needed to affect the surprise of the next token, it is mostly valid if all tokens are relevant and are in the same context. I don't understand any of this. Okay? I don't understand any of this, but I will say that my brain is filled to the brim a little bit. Filled to the brim. So, I can't understand any of this math. Some of these concepts, interesting. Okay? Understanding how we have a long-term memory, very interesting. Thinking about surprise being an element to when you want to memorize something, interesting. The concept of forgetting memory is interesting. The concept of dividing surprise up into two separate elements, past surprise and momentary surprise, interesting. So, I can't quite understand what it's all saying, but hey, we made some progress. We learned some things. So here's how to parallelize long-term memory, memory of the context, Mac architecture, persistent memory. Look at how to incorporate memory. Now we're getting experimental setup. We're getting into the cool stuff. We're showing off the results here. We got Titans on top. Look at that. Look at how much the Titans do better as the sync length goes up. Oh my God. The most references ever. The most references ever. Okay. Interesting. I think it's probably a good place to stop. Learned a bit. Brain hurts, definitely. I mean, we can try and read these papers even if we're not smart enough to know the math and we didn't go to school and we just happen to learn this AI on the streets. I'm just hooking up APIs on the streets. But still, it's definitely making my brain turn a little bit. I'm gonna probably try and find some more fundamentals of math I can like learn to actually keep understanding things more in the future. But really, what I want to know is just how can I use it? Share some code. Okay, give me an API and an API key. Let me hook that thing up. So I'll be back tomorrow. We'll talk about more stuff: AI, AI agents, code, all that fun stuff. You got anything you want to talk about? Write in the comments. Thank you.